Good afternoon, everyone. Can you hear me? Am I audible?
Yes,
Are you able to see the screen?
yes.
Okay. Yeah, so as I mentioned, I just uh, mainly wanted to help you with any doubts that you have. So if any of you have any doubts, you can ask me.
I had a doubt from the class exercises, one of the class exercises.
Okay, like for first problem set or second problem set?
First problem set. Um,
Okay.
Question 4. Um,
What was the question?
so we have to prove that for any sub-Gaussian random variable, the
Mhm.
expectation is 0 and the variance is less than sigma square.
Okay, so did you look at the solutions which I uploaded?
Um, oh, okay. Uh, I missed the solution. Um,
Okay. Essentially, you have to just expand it using the e power lambda's expansion. You know this, right?
yeah, yes.
So you expand like this, and then you get some polynomial. Like you'll get some thing like this. Like you'll get lambda into something plus lambda square into something plus so on less than or equal to zero. You can get it like this if you just use this. Like this is the definition of uh, for all lambda, right? This is the definition of sub-Gaussianity, right? You just use the definition and get some inequality like this, and then what? Like here, what you'll get is expected. It's I think like in the first thing. So, so then what you will do is you will divide by let's say lambda on both sides. If lambda is a positive number, let's say, if you divide by lambda on both sides and then equate and then take lambda equal to 0, lambda tends to 0, then you get expected h less than or equal to 0. Then instead of dividing by positive lambda, you divide by negative lambda and then again 10 lambda to 0, then you'll get expected it's greater than or equal to 0. So from both those things, you can conclude that expected h is 0. So roughly the idea is like this. So I can show you if you I can show.
Yeah, I got it. I used another method, like I took the natural log and then I used Jensen's inequality.
Okay.
Yeah, I think that that gives the same thing, like so it comes out to be bounded by lambda square, sorry, lambda sigma square over 2, and then I think I can use the same thing, right? Like it's bounded by lambda, so if lambda is greater than 0 or less than 0.
Okay. Yeah, you can check the solutions also if you want
Okay,
for this approach. Yeah.
okay. Thank you, sir.
Yeah.
Divided by hello?
Yeah. Tell me.
You divided by lambda square, right? And
Uh,
then you set lambda to be 0 or
let
something.
me open the solutions. I'll show you. Which?
Question 4.
Huh?
Question 4.
Okay.
Next
Yeah.
page. The next page we have.
This part
No, no,
for the lambda square,
the-
for variance or
uh,
for variance?
uh,
Okay.
you divided by lambda square here, and
Yeah.
then in the next part you set lambda to be 0.
No, this is true for any lambda, right? Like the first equality is true for any lambda, right? So you divide by lambda square, then you get the second equality. Again, this is true for every lambda, right?
Like when I'm dividing by lambda square, I would assume it to be non-zero.
No, you need not use the same lambda there and here, right? No, like this is like this second inequality. Is it not true for any lambda?
I was just thinking, as long as it is lambda is not equal to 0, the second inequality will be.
Okay, then you just turn lambda to 0 instead of setting it equal to 0. You take limit lambda tends to 0.
So,
Right? That should be okay, right?
yes,
Yeah, so you can just think of lambda as some very small positive number. Lambda square, like you just take lambda square, divide by lambda square and turn lambda to 0. So you mean our second inequality is true only if lambda square is not equal to 0. That's why you are asking this out, right?
yes, sir.
Because we're dividing by lambda square, so it is true only for lambda square not equal to 0. Okay. Yeah, you can just turn lambda to 0. Maybe that's a slight mistake. Yeah. That is okay, right? Like limit turning the limit lambda tends to 0 should be okay, I think.
Yes, sir. It will be fine.
Okay. Anyone else has any other doubts? Or you yourself either from the class or
I had a question from the notes on um, this uh, CS6046 notes on bandits,
okay.
page number 2,
So it's about an exercise or some concept.
concept.
Okay.
The multi-armed bandits, the notes which you uploaded.
Okay. Which page?
Page number 2.
This one?
Yeah, yes. So this equation 1.1 below.
Okay. Lemma 1.1, no?
Yeah, the in the proof, like
Of
I
this
have
lemma.
some doubt in the notation.
Okay. So this notation is a little bit different than our notation.
Yeah,
Yeah.
uh, I mean in equation 1.1, so how did they um, get from the previous step to the next step? Uh, like how did they get to equation 1.1 from the immediate previous step?
Okay. Okay, so I did not look at this. Maybe I'll just look at it and see if I understand. Like the Sn is the sum of random variables sum to n, and then ht is ht. Right, equal to. Okay, so we use the fact that okay, expected Sn equal to internal expected. So it's so for any expectation, what you can do is you can condition and uncondition it. For example, let me see if I can write it here. So is it visible whatever I'm writing?
Yes.
So generally, if you have something like expected x, this is nothing but expected value of expected x given y for any y. This is a standard result which says like if you want to compute the expected value of some random variable, if you want you can condition on something and then uncondition on it again. Like this is
So,
what they've used, right?
uh,
So
okay.
if you
So,
call this whole thing as x, this is y, this is what they've used, right?
yes. So, like X and Y
Can be
are,
any.
oh, okay. Okay.
So it is like you are conditioning and then removing the conditioning.
Right.
So maybe I can. I'm just thinking if I can explain through an example, but this is a standard result. I can think of it.
All right. Okay. And uh, I had another one on page number 4.
Okay.
The beginning part,
Page number
page 4,
4.
page 4. Yeah.
Okay.
So, so how did they guess from the first equation to the second one? Like they changed the expectation to the probability.
So where on this one to this one, no? Like
Yeah.
the first line to second line.
Yes, they changed the expectation to probability. I did not understand that.
So this regret till time n is m into delta I. That is the first m times we explore each term once. So that is that m into sigma delta I. Then in the remaining n minus mk times, we are summing over delta I into number of times delta I into which arm is being played. Whether some particular arm is being played in that round or not, right? Okay. So what is the question now?
How did they change the expression from expectation to the probability?
Like the expectation is of an indicator function, right? I- Indicator function is one or zero, right? The values are one or zero.
Yes.
So then what is expected h is h into probability of h sigma. Sigma h into probability of h, right?
Yes.
So just so sigma h into probability of h. So if this is your h, what are the values that h can take? Either 0 or 1, right? So 1 into probability of h, like probability that it's equal to 1.
Oh,
It's
okay.
0 into probability h equal to 0. So this will go off. So only this thing will remain because it's an indicator value, right?
Yeah, I I got it.
Yeah, for indicator random value, expected value is nothing but the probability of 1 in being 1. Okay.
Yes.
Okay. So anything else? Anyone else has any doubts? So we have uploaded problem set 2 and assignment 1. Did you guys get a chance to look at them? Yeah, so this is the problem with the online tutorial. No one speaks anything and I can't even see you. So, so if you have any other doubts, you can ask me. Otherwise, we can close it. Like, is there any topic from the class that you want me to tell you again? Or is there anything else you want to ask? So one thing I just wanted to tell you, maybe in the problem set too. Generally, I have given some standard inequalities which we might require for solving the problems, right? In problem set one, I have given some standard techniques which can be used, right? In that, maybe this is also one thing which you can use, like the definition of convexity, like a function, for example, f of x equal to h square. Let's say this is our function. This is a convex function in the sense that if you if you take any 2 points on this, let's say you take a point x and point y, like you take any point x and y, and you look at the if you draw those, if you connect these 2 points by a line, then the line will always stay like this line will always be greater than or equal to the function value. Like the function value is this, right? This line value is always greater than or equal to the function value in for any number between x and y, right? So this is formally the definition of a convex function is f of theta x plus minus theta y is less than or equal to theta into f of x plus 1 plus theta f of y, where theta belongs to 0 comma. Okay, so this is the definition of convex function, right? So this is nothing but the value of the function for any number between x and y, like this curve, and this is less than or equal to. This is nothing but the uh, value of the is correct. Am I writing it correct? Anyway, so all that I want to remember is there is this concept called convex function, which you can use to, uh, which might be required to solve your problem set. Okay.
Yes,
Yeah.
sir. So I had another question.
Yeah.
So in the class exercise, you asked to prove like for any bounded random variable if uh, between a and b it is b minus a over 2 sub Gaussian. So I was
Hmm.
actually looking for a proof, but like can you
Actually,
explain the proof once?
that is a little bit more involved. Uh, like so for like first of all, you understand that the expectation. Sorry. What is that we want to prove? We want to prove that e power lambda x is less than or equal to h of lambda square sigma. Something like this. This is what for some sigma. This is what we want to prove, right?
Yes.
I think the first thing would be you look at all any distribution between which is bounded between a, like let's assume that expected x is 0. Like if it is not equal to 0, you have to center it. Like you have to consider x minus expected x, because we already know that for any Gaussian sub Gaussian random variable expected x is 0, right?
Yes.
So you can assume that already expected x is 0. If not, you just define a new random variable y equal to x minus expected x. Who's expected? Like if you define like this, then expected y will be 0, right?
Yes.
And it will just shift. The ranges will just shift, right? Like your y will belong to a minus expected x to b minus expected x. So the difference of the interval is the same, right? Still the same. Like this is b minus a, this is also b minus a. Like either for x or for y, the length of the interval is still b minus a. So all that you have to prove is you have to prove that sigma equal to b minus a by 2 is the sub-Gaussian property. Like you have to show that for this sigma, the sub-Gaussian property holds, right? So either you just take expected x to be 0, or you can define y and do it. So it doesn't matter. So whichever way you want to prove. So for simplicity, let's assume that expected x is already 0. So if expected x is 0, Now, if you want to understand this, we want to prove for any distribution between A and B, right? Like which has bounded support from A to B. So the first step would be to understand that if you look at e power lambda h, for all, like for every distribution of h, you'll get a different value, right? So you can show that the worst case, like the maximum value of this, if you look at, if you take the maximum over all possible random variables which lie between A and B, you can show that this occurs when the distribution has only, if you take a distribution which takes value B with some probability, and let's say A, let's say the H takes only these two values, and you have to select these two values such that the expected sum will be zero. So if you carefully select these probabilities, like this is with probability P, with probability 1 minus P, let's say, you can select P, right? From this equation, you can find the P, right? So what we can argue, if we argue properly, what we can show is the expected value of e power lambda h. If you look at all distribution sets which has bounded support, this distribution will have the highest expected e power lambda h. So then what you can do is you just show that for this particular distribution, expected, you just show that this particular distribution satisfies expected e power lambda h is less than or equal to this thing. Then this will hold for any distribution which is bounded. So you can think of the proof in two steps. The first step is to show that expected lambda h is of any distribution x which is bounded between A to B is less than or equal to expected lambda h of this particular distribution. Then you show that this particular distribution is B minus A by 2 sub Gaussian. So that's the high level idea. So maybe I'll, like, the proof is a little bit more involved. It's okay if you don't be able to prove it, but this is the high level intuition. I'll try to give the solution for this and upload. But did you get
Okay.
the overall approach?
Yeah, I understood.
Yeah. So this P is uniquely defined, right? Based on this expected H equal to 0. So you are looking at some particular distribution and then proving the subquotient for that distribution, and you are arguing that any expected lambda H, e power lambda H is less than or equal to this particular distribution's e power lambda expected. Yeah. So that's the high level approach.
Yeah, I got it.
I think to prove this particular thing, that this expected e power lambda h for any thing, you can use the uh, convexity property.
Okay.
Yeah, so that's roughly the high level. Mhm. So anything else? So in the assignment, I think the first part is on just verifying Chernoff bound, and the second part is on simulating ETC and UCP. So, like for the UCB, for the ET, for the part B, we have given a Jupyter notebook uh, uh, where some basic code is given. So that code you can either use it, or you can, if you feel comfortable writing it on your own, you can do that as well. Like maybe for some people, just writing it on their own is much easier than going through the code which we have given. So you need not even look at that code which we have given. You just look at the problem statements which are there and just start coding on your own. In case you need some, if you feel like it having some base code is useful and you're comfortable with object oriented programming like classes, etc., then you can use the base code which we have given. Otherwise, you can write your own code which you are comfortable with. But just make sure that you use Python so that it is easy for the instructors, like TS, to correct it.
Yes, sir.
Yeah. Yes. So that's all. Anything else you have?
No, I think that's it.
Okay. Okay. Thank you.
Yeah, thank you, sir.
Mm.